Hi, I'm Tommaso, PhD student at Graz University of Technology.
And I'm Daniel, also a PhD student at the Graz University of Technology.
Welcome to Bridge the Gap, the physics-oriented podcast,
in which we give insights into various research topics and the life of scientists.
And by the way, if you want to contact us, you can drop a line to our email address bridgethegap@tugraz.at. Hey Daniel!
Hey Tommaso!
Good news for you. Today we will start with a poem we wrote instead of the jokes part. Happy?
Very much!
Let's begin then. From fiery birth, the sun begins its flight.
A cosmic force that paints the heavens bright.
The solar wind then sweeps with boundless grace.
A breath that sends particles in endless space.
Magnetic fields will twist and flare, unseen.
And shape the stars, both fierce and keen.
From their fires, new elements take form.
A colorful chaos that fuels each star's storm.
Some stars will grow, giants in the sky.
Then shrink to white or brown and slowly die.
While others burn with uncontrolled glow.
And burst in flames, a brilliant final show.
Their pulse will fade, only stardust remain.
A legacy of light and dark in a vast domain.
So Daniel, you know what's the thing I like the most about our short poem?
Obviously that I don't have to suffer through the jokes.
Well, in fact, that it gives me the opportunity to introduce the jokes part.
You tricked me!
Well, so hold tight there. How do you call a 3D picture with round edges that glows in the dark?
Non-existent?
Well, no, a photosphere, of course, like the sun's outermost atmosphere.
Right, because everyone knows spheres have edges, right?
I hope you appreciate the magnitude of my jokes. Like stars, they're the brighter, the more negative their magnitude.
And for sure the magnitude is pretty negative, that I can confirm.
Aha. Anyways, today's topic, as you might have guessed, is solar physics. With us to discuss about this, Alexander Shapiro, professor at University of Graz. So, today with us, Alexander Shapiro from the University of Graz. And Alexander, can you introduce yourself, your background, field of expertise? Stage is yours.
So, it's a pleasure for me to be here and talk about exciting areas of stellar and exoplanetary physics. So, I was born in Soviet Union in Leningrad. I also was a master, or how we say in Soviet Union, specialist scientist, student in the St. Petersburg State University. Then I immediately moved to beautiful Switzerland. So I was doing my PhD at ETH, so in Zurich. And then after that, I had like 5 or even 6 year postdoc stay right in the heart of Swiss mountains in Davos. So it's a very nice place, very famous place, but sort of a village, well, with a number of science institutes. And then I moved to the Max Planck Society, to the Max Planck Institute for Solar System Research in Göttingen, where I was basically became finally an independent scientist. So I led a group there since 2017, so basically means for 7 years. And then this October I came finally to Graz, to Austria. So I have a long tenure in German-speaking country. Now only Liechtenstein, is probably missing.
So to start maybe, could you explain to us sort of the internal workings of a star, maybe of the size of our sun?
So the star is basically a huge ball of gas, so mainly hydrogen and a little bit of helium, a small mixture of other elements. And then basically gravitation pulls this ball together, and it creates a huge pressure in the center of this ball, and pressure in temperature so high, like temperature is roughly 15 millions of Kelvin, that nuclear reactions start, so in the center of the sun, we have burning of hydrogen to helium, and that basically sustains this pressure, so the energy being released, and that sustains the solar luminosity, and there are a lot of interesting physics and untrivial physics involved in that. Like, for example, one of my favorite statements, which is not that trivial, is that Sun and other stars, they have negative heat capacity. And that appears to be extremely important for us being alive and for Sun, not exploding immediately. So what it actually means? It means that when the Sun loses energy, its temperature would actually increase. Yeah. So what actually happens? It loses a little bit of energy and then it contracts. And then gravitational energy, so basically leads to the extra release of energy, yeah? So, and it basically means that the Sun has negative heat capacity, and then why it's important, yeah? So there are a lot of instabilities, for example. Imagine that for whatever reason, temperature in the center increased by a couple of Kelvin, yeah? Then efficiency of nuclear reactions would dramatically increase, because nuclear reactions, they hugely depend on temperature. And what then might happen is, temperature grows, efficiency of nuclear reactions increases, and that's sort of, like a runaway nuclear burning, yeah? So the Sun will be gone in seconds, yeah? And such process actually happening. I mean, we will discuss it probably a little bit later, yeah? But then on the Sun, it happens totally different. Nuclear reactions, they get more efficient, energy is being released, and it leads to the drop of the temperature. Drop of the temperature, nuclear reactions are less efficient. And that's why basically, the Sun, can and will basically last for 10 billions of years. Yeah, so all instabilities are basically dumped.
That sounds interesting. Is there a convenient classification of stars, maybe according to their mass, and what does that mean for their evolution?
Yes, so mass is basically the most critical parameter. Yeah, so mass, and it's also easy to understand because mass defines conditions in the core of a star, pressure and temperature, basically from the hydrostatical equilibrium. Yeah, so the conditions in the center should be capable, of maintaining all this huge mass on top, yeah? So mass defines pressure temperature define efficiency of the nuclear reactions, and then nuclear reactions, efficiency of the nuclear reactions defines luminosity of a star. So mass is basically the main parameter. There are also age, when stars age, they gradually getting a little bit bigger, like our Sun is gradually getting a little bit bigger. So another parameter which is important, what we call in astronomy, it's log J, which basically means acceleration of gravity on the surface, yeah, which defines how big is the star. And then there is also metallicity of a star, like how much elements heavier than helium. So in astronomy, we have very funny classification of elements. Yeah, there is hydrogen, there is helium, and everything else is metals. Yeah, so it's pretty different from what normal people
about
notice.
this.
And this small, mixture of metals slightly affect the condition in a star, but otherwise it's mainly the mass. Yeah, so there are stars much less massive than the Sun, basically down to 1/20th of the solar mass. We call them red dwarfs. There are also stars which are much more massive of the Sun. So I think maximum what is possible is now believed to be between 150 and 300 solar masses. Yeah, and these stars are much more luminous. And I think one of the stars now recently was discovered. They claim that its mass is like 250 masses of the Sun. Yeah, so that's pretty
large.
Kind of a beast. Yeah. Yes.
Why is there a limit on the mass, or is there a limit of the mass of and why is there a limit?
So the point is that if the mass is larger than the so-called Eddington limit, yeah, then temperature and pressure in the core would be so high that nuclear reactions would be just, tremendously effective. Yeah, like we would have huge release of energy. And then the star would also radiate a lot. Yeah, so this energy should be somehow, transferred through the star. And the pressure of this radiation would be so high that it would basically, pull the star apart. So the luminosity gets so huge, yeah, that gravity cannot anymore basically maintain the equilibrium. So this is called Eddington limit, and there are a number of revisions of this limits, also taken different second-order effects into account, and as far as I remember now, it's exactly believed to be between 150 and 300 solar masses. And the most massive stars, like this beast, what I just mentioned, they believed actually to be products of mergers. So it's very difficult to form, immediately such a massive star. But under certain circumstances, stars can collide and, not explode, maintain the stability, and then we would have sort of stellar cannibalism, and then such a massive stars appear.
What happens when the star finishes its fuel?
Yeah, there are a number of very interesting processes. Like, it heavily depends on the mass of a star. Let's first, for example, focus on a sun. So what would happen on the sun? The core of the sun would gradually contract. The outer layer would in opposite extent. And then at some stage, basically, we don't have any hydrogen left, so we have just a small core, and then hydrogen would start burning in a shell around the core of the sun, and it would basically, the sun would go what we call subgiant branch, because it would be bigger, and since it's bigger, basically luminosity is higher, so even so the temperature, as far as I remember, would drop a little bit, but the increase of the size would basically lead to the increase of the luminosity. And then at some stage, there is no possibility also for no hydrogen left for the burning in the hydrogen shell. Some hydrogen, of course, still remains in the outer layers, but temperature and pressure are not sufficient for the nuclear reactions. And then extremely interesting process would happen. So the helium in the center of the sun would be degenerate. So pressure would not anymore depend on temperature. And then this argument with negative heat capacity actually doesn't work anymore, because for the degenerate gas, the heat capacity would be positive, And then there will be very exotic event, which is called helium flush. Because what then would happen, that helium would start to burn somewhere, not probably in the core, but somewhere, in the outer layers of the core. And then exactly this catastrophe, what I was talking about, would happen, So it would start burning, temperature increase, more and more helium start to burn, and then I think it takes probably hours or days. So we have huge, or even minutes. No, I think it's actually a couple of minutes, So for the couple of minutes, we have this huge explosion, basically, and the rate of energy production during these minutes is basically comparable to the entire energy production for this time from the Milky Way, So that's really huge. But now the coolest thing, that all this energy, it will not be really radiated, but it would actually go for removing degeneration of the core. So we wouldn't see any photons, but what would happen, like huge energy would be absorbed by the core, and core will become again like an ideal gas. So this super exotic and interesting process, actually nobody's seen with observations. That's sort of predicted by models. We know that, stellar evolution looks exactly as predicted by the models. So I think we believe that this really happens, but nobody have seen it until now. Then the core will become like ideal gas again. And then there will be burning of helium to carbon and oxygen, basically. So that's the next reaction. And then the sun would move what we call horizontal branch. So it would be, again, much more luminous than it is now, and also much bigger. And then for the sun, for more massive stars, there might be other nuclear reactions, so basically up to the iron. But for the sun, the temperature, the mass is not enough, basically, for these other elements to burn. So we wouldn't have burning of oxygen or burning of carbon, for example. So then what would finally happen, that helium reaction would stop, no more helium, we have just carbon-oxygen core, it will become unstable, the outer layer of the sun would expand even more, and we would have like a nebula, and the inner layer would contract and form a white dwarf, like a star without any nuclear reactions, which basically just emits energy because of the inner thermal capacity, so there are a lot of temperature, and this white dwarf would exist, indefinitely, basically, so also the amount of energy stored in white dwarfs is pretty large, so they will be basically, always emit something, for a very long time. And that happens with the sun, basically. Then for more massive stars, it's getting even more sort of interesting, because for them, one can have also further reactions, like carbon, oxygen burning, and the star would look a little bit like an onion, so there will be shells with different elements, like burning, and in the end, we would end up with an iron core and, a shell of different elements, what we call around iron peak elements. So that's elements which can be produced by the sort of nuclear reactions. And at some stage, the mass of the core can become so large that iron would start capturing electrons, because pressure is so high that, one can even understand that from a very, very basic point of view. There is no space for iron and electrons together, So iron would start capturing electrons, neutrons then will be formed, the core will contract, and at some stage become unstable. It will become unstable, and that's what causes supernova explosion, because there will be huge release of energy, And then depending on the mass, it would either go to a neutron star, or even for more massive star, it will basically go to the black hole. And energy would be released, gas will be sort of, so it would be like really huge explosion, For the sun, we are lucky. It will never happen, but for other stars, it might become...
Well, lucky us.
Yes. Well, there are many other dangers, of course, on the way, but...
I have a curiosity, if I may, since you mentioned that there is this shells, concentric shells in the star, in the core of the star, basically. And then we stop at iron, the way I understand. But then on Earth, we have something which is heavier than iron. So how do we get all the elements that we have on Earth?
Yes, that is a really good question. So first of all, why we stop on iron? Because fusion reactions are not anymore efficient. Because if, for example, we would draw, we would look at the energy of the nuclear core per particle, it would increase with the weight of the core, with atomic number, till iron, then it would start decreasing. And that's actually also with a very simple logic, easy to understand, because what keeps all the particles together, it's a strong interaction, Strong interaction is extremely, it only acts on a very small distances. You slightly increase the distance, interaction is gone. So when we have small core, all nucleus are close to each other. They are very nicely glued together. But then when we have a huge core like iron, like huge nuclear like iron, then basically we have different protons on a large distance to each other, and they are not anymore glued. So the nuclear is basically unstable, So that's why, it doesn't make, energetically, it doesn't make any sense to create in a fusion reactions something more than iron. So what happens, how all the elements on Earth are created, that are called slow and rapid processes of capture of neutrons. So it's a totally different reactions, like A process, fast process. I think it's called A rapid. That's why how it happens, I think, during supernova explosion. And S process, if I'm not mistaken, it also happens at the late stages of stellar evolution and in the environment, basically in the outer layers of a star. So it's not something what is created in a nuclear reactions in the core. And that's also quite exciting, because I think some elements, they can be only produced with this A process. And then basically it means like we have these elements in our bodies, so we are not just created of elements up to the iron, which basically means that some atoms, and actually a lot of them in our bodies, they were born during explosion of supernovas. So sort of, we are remnants of supernova explosions. Exactly. Well, extremely violent not just stars like the sun, but something extremely violent, so...
No, that's really fascinating.
Yeah. So you see, violence is in our blood, so
Stars are also used to detect exoplanets, right? Can you tell us how this works?
The first ever exoplanet, actually, not that many people know about it, so it was discovered not in 95, with this famous 51 Pegasi B case, which was a Nobel Prize of Didier Queloz and Michel Mayer. But the first exoplanet was actually discovered 3 years before. It was exoplanet orbiting pulsar. And what people basically noticed is that the period of a pulsar, so pulsar is a star which emits basically energy on a very regular amount of times, with a very constant period. And what was noticed that this period actually exhibits small variations. And it was connected to the Doppler effect that's allowed to calculate mass of the component. So Doppler effect simply because the star and planet rotate about a common center mass. So this allowed then to determine mass of a second body, and the mass appeared to be smaller than one can expect from a star. So that was first ever discovery of a exoplanet. But of course, the excitement, real excitement came in 95 with this discovery of hot Jupiter around star on the main sequence. So star where we have to some extent solar-like star, where we have hydrogen burning to helium, So, and after that, of course, the field boomed, And how it was done? The technique was actually quite similar, the discovery of the exoplanet around pulsar. So, the radial velocity of a star was measured very precisely, And the variations of this radial velocity, I think it was roughly 60 or 70 meters per second, have been detected. And these variations were basically again sinusoidal. And that was again attributed to the rotation of a star around common center mass. And then mass of the planet was calculated, and it appeared to be a little bit below, as far as I remember, half of the Jupiter mass. And that's basically, so it was first planet around to some extent solar-like stars. I'm saying to some extent because different people have very different definitions of solar-like star. In my area, for example, people sometimes argue whether it sun-like stars, solar-like stars, solar twin, whatever, so one should be a little bit careful not to offend anybody's feelings.
And what are the challenges in detecting exoplanets? Because I can imagine that it's not very easy. I mean, it's like spotting a fly on.
Yes. So I think what is extremely I'm mainly stellar physicist, and I got in a way tremendously lucky because to study planets in the solar system, we look at these planets, To study stars, we look at stars. To study the sun, we look at the sun. But it's not possible with exoplanets, exactly as you say it. Direct observations of exoplanets are very, very limited. So now to characterize and discover exoplanets, one should look at the host stars, And then there are a lot of interesting effects come into play. And these effects were even, I was recently looking a little bit at the literature around this first discovering of the 51 Pegasi. Already at that time, people were concerned, for example, by the stellar activity. So there have been speculations that 51 Pegasi b is not a planet, but these variations in the radio velocity are caused by huge spot on a star, because it would to some extent act similarly to exoplanet, introducing these variations in the radial velocity. Because what one should keep in mind that stars, they are just, they're a ball of gases, but not really quite ball of gases. A lot of effects happening on the surface. There is, for example, convection, so this bubbling pattern, there are magnetic features, there are flows associated with magnetic features. And these flows, they have, let's say for the star like the sun, order of magnitude of kilometers per second, So when we look at the surface, we have a lot of motions with the order of magnitude of kilometers per second. And here we are up to, this first discovery was, I think, 60, 70 meters per second, So it's much smaller velocity. And then, of course, the good thing is this huge velocity of the star, they're averaged out. So if you have, some gas moving up, there will be also some gas moving down. Yeah, so it sort of averages out, but doesn't averages out perfectly well. And that's especially the case when we have some magnetic activity, magnetic features on stars. So they have been suspicious that, this exoplanet might be not a really exoplanet, but spot, but it was actually really nicely shown that it's not the case. So I think very soon after, already in this very first paper about 51 Pegasi b, it was very clearly explained why this cannot be a spot. But then there have been other cases, for example, when the star showed the sinusoidal bifurcation, and for that cases, that was actually a spot. Yeah, so I think there was even paper like no planet for HD tratata for whatever star. And then, when one looks at the signals from this 51 Pegasi and that star, they're so similar actually. But in one star, it's caused by planet. On another star, it's actually caused by a huge spot. And this sort of propagates now the life is getting, in this sense, even more difficult because the discovery was done like 60, 70 meters per second. Yeah. Then accuracy of the measurements of the radio velocity started to improve tremendously. Like I remember when I was a student, I think it was like 4 or 5 meters per second. And our professor wanted, to demonstrate how small this number is, basically, by running in the room. Yeah, he's saying, imagine if I'm a star, we now have telescopes, we now have instruments which would detect such a velocity for stars which I know hundreds of light years away from us. Yeah, so that is, then it continued to improve. And one number to keep in mind is what is needed to discover Earth-like planet around, or let's even say now Earth twin, like real Earth around the sun at 1 astronomical unit. So for this, we need precision 9 centimeters per second. Yeah, so it's like extremely slow. Yeah, and then the unbelievable, I still find it very difficult to comprehend. It's like really science fiction, but we have instruments which are capable of it. So somewhere, I think 10 years ago, the instrument crossed the 1 meter per second barrier and now really go to this 10 centimeters per second. But surprisingly, there are very few discoveries below 1 meter per second. So instruments are capable of discovering smaller values, but there are very few discoveries. And this is attributed to the activity of a star. Because 1 meter per second is, for example, exactly the level of these residual signals what we have on the sun. So it sort of, was transition from the instrument limited era, now let's say to the theory or understanding limited era. Yeah, so that's exactly what now, there have been huge investment, fantastic work basically by observers to get to this 10 centimeters, so 9 centimeters per second. And now it's turned for theoreticians, basically to understand what to do with this data. Yeah.
But how can one even distinguish this?
The main idea is that how people measure radio velocity, they look at spectral lines. Yeah, they basically identify, let's say, 2,000-3,000 or even more lines in a solar spectrum or in a stellar spectrum, yeah, and then they measure shifts of these lines. And how it's done, that in one line, it's very difficult to measure, yeah, basically. So all the information from these lines is combined together. And in the end, with whatever different mathematical techniques, we end up, let's say, with one average line, which is average of this several thousand of lines. And then this line is used basically for the velocity. And now there is a fundamental difference between the Doppler effect, yeah, which is people that we are looking for when we look at exoplanets, and stellar activity. So Doppler effect would affect all the lines in the same way. So delta lambda over lambda would be constant. Stellar activity or granulation would affect lines very differently. For example, it would affect differently iron 1 and iron 2 lines. It would affect differently, let's say, titanium and iron lines. And then idea, basically, yeah, is to do like not to average all the lines together, but sort of take into account the information that the lines have different sensitivity. And it's not that super trivial because, well, that demands really deep understanding of what's like to basically predict which lines are sensitive, which lines are less sensitive. It demands a very deep understanding and very accurate modeling of the stellar atmospheres. So that's exactly basically the area what we are doing here in the University of Graz. Yeah, trying to understand what to expect from a star.
And does it work? Could you find?
That's a really good question. It works in theory until now, yeah. So I think it was not yet. So we are developing some methodics together with our colleagues. So like myself and like my group, it's better not to be in the vicinity of the telescope. Yeah, so we're real theoreticians. Yeah, but we have our partner group in St. Andrews University, and basically we work together with them. So until now, we do not yet know whether the method we developed really, let's say, works in the field. We have hopes, but we do not know. I mean, it is clear that this is the direction to go. Yeah, so not this year, not next year, not next 5 years, but sooner or later, this
will be there.
Should work.
Sure,
Yes.
I mean, it takes a long time to develop.
Exactly.
As you say, it's highly non-trivial.
Exactly.
I mean.
Yeah.
So in a sense, also before you mentioned that for rocky planets, if I understand correctly, so similar to Earth, the detection is more difficult due to this residual signal, right? So in a sense, we're biased.
Exactly. Because the point is, well, what matters is mass, yeah? So like, for example, Jupiter around the sun leads to a much stronger velocity than Earth around the sun, yeah? So it's as easy as mass, yeah? The more massive is the planet, the more easy is to detect it, yeah? Well, with radio velocities. Now also, like we talked a little bit about, we can talk a little bit about different methods for detecting and characterizing exoplanets, because sort of gradually this era, let's say, of blind radio velocity searches is coming to an end, yeah, because it's pretty expensive. So what now, basically, the current state of the art, it's transit photometry missions or transit spectroscopy even missions. It basically means that we try to detect transit of a planet across the visible stellar disk, yeah, so it would lead to the temporary darkening of a star for like a couple of hours, yeah, and that's sort of now is, let's say, one of the main technique for discovering exoplanets, and it allows to discover the radius of the exoplanet. Then if the exoplanet, which is discovered with this transit mission, followed up by the radio velocity surveys, yeah, one can also get mass. If one has mass and radius, one has density. And if one has density, that's exactly what is needed basically to understand what exoplanet we are dealing with, yeah, like to prove that it's rocky, or to prove that it's, like Jupiter-like or whatever, yeah. And one other absolutely exciting direction, I couldn't even believe, like when I first time have heard about that, I saw that, it's not possible. I mean, these people cannot be serious. Because, think about it, the first exoplanet was discovered in 1995. And already, 6 years after that, the method was proposed for characterizing atmospheres of exoplanets, yeah? And now, as I said, I was very skeptical in the beginning, but a very interesting sort of fact to think about that the flagship of modern astronomy, yeah, it's a James Webb Telescope, yeah, and now what James Webb Telescope does basically a quarter of its time, it's actually trying to characterize exoplanets, atmospheres of exoplanets. So what it does basically, it measures the transit of exoplanet at different wavelengths, and then the visible radius of the exoplanet would depend on the wavelengths, because let's imagine Earth. If we have transit of Earth around the Sun at the wavelengths where the Earth's atmosphere is transparent, then we would just see the rocky body, yeah, basically whatever, 6,370 kilometers, yeah. Now imagine that we look somewhere in Chapuis bands, or, like somewhere where ozone layer absorbs photons, then we would have plus 50 kilometers, or even a little bit more than that. Yeah, it depends on the exact geometry. So when we observe at the wavelengths where the atmosphere actively absorbs or scatters photons, the planet would appear a little bit bigger. Yeah, and then just what people are doing, they're doing so-called transmission spectrum of a planet. So it's nothing else as a dependence of the radius of a planet on wavelengths. And this allows actually to understand what is the chemical composition of the atmosphere of planets. That's really, for me, it's thinkable. Really, because
it's crazy.
Absolutely. Yeah. I mean, of course, there are issues. There are, like it's inverse problem. It's difficult. So there are many issues. But still, some discoveries that crystal clear. We yet to, like, what is the main thing James Webb is doing? Idea is to discover atmosphere of rocky worlds. This is not yet done. There are a lot of information about atmospheres of hot Jupiters or like super Earths. Rocky planets are not yet. There have been some claims, but they are argued. Yeah, so they're quite debatable whether it was done. Yeah.
One point, I guess, this could be used for is to find molecules that show signs of life, right?
That's extremely hot topic, exactly. I mean, to discover basically what is called biosignature, yeah? So to discover gas, which is not in a chemical equilibrium, if only like, if life is not there, yeah? So something which is out of the equilibrium, yeah? That is, of course, a next step after discovering atmospheres of rocky planets, yeah? There are also some speculations that it might be of subgiants. Super Earths, yeah, like in atmospheres of super Earths, some floating life or whatever. But of course, a huge discovery would be first atmosphere on a rocky planet and then biosignature. Yeah, so
that's very interesting. Yes. Well, what do you think are the chances of finding life on exoplanets?
I tend to be usually very optimistic, but one should be a little bit cautious, like a fantastic example is, I think a couple of years ago, there have been quite a lot of coverage also in the news about the discovery of phosphines, I think, in the Venus atmosphere. Yeah, so there have been some hypotheses that actually there are biosignature in the atmosphere of Venus. Then there have been a couple of papers which say, nope, it was wrong. Then there have been papers which show, no, it was correct. So I don't think it's actually even a close topic now. I do not follow it, actually, so not really to judge, but it is clear, like think about it. Venus is next door to us, yeah? And still people
we don't know.
Exactly. Still people are seriously arguing about it, yeah? So it's a valid scientific question, yeah? So now think about stars and planetary systems which are far away, yeah? So sure, I mean, I'm pretty sure that there will be, there have been already a couple of claims that there are atmospheres. I'm pretty sure there will be also claims for biosignatures, if they were not already actually. That is absolutely clear. How serious and how trustable are they? That is totally different question, yeah? So that's going to be difficult.
Then we thank you for your time. Thanks for being here, and see you next time.
Thank you. It was a pleasure for me.
Thanks for listening.
And hear you next time.
And by the way,
if you want to contact us, just send a mail to bridgethegap@tugraz.at.